Yeah, hello everyone. Myself Akshay Jajoo, and today I'm going to talk about SLearn, a case for task sampling based cluster job scheduling. This work was done in collaboration with Professor Charlie Hu and Professor Xiaojun Lin at Purdue University and Dr. Deng from Google. In both private and public clusters, jobs arrive online and compete for shared resources. These jobs have diverse runtime requirements and diverse SLOs like meeting a deadline or minimizing the runtime. So together, these two factors make optimal scheduling difficult. And knowing the runtime requirements of these jobs will help the cluster scheduler to optimize the performance. However, these jobs are non-clairvoyant, and their runtime properties are unknown. So this lack of knowledge of runtime requirements make optimal scheduling further challenging. An effective way to tackle these challenges of cluster scheduling is to learn the runtime properties of pending jobs. And the widely used approach for learning runtime properties is to learn from historical data of past executions, that is learning in time. At a high level, history-based learning is a straightforward approach. Take the past execution log and process it to get a predictive model. Then, when a new job arrives, pass it through the model to get its estimated runtime. Many works have been done using history-based learning. These history-based mechanisms have improved over time and have gotten more sophisticated in the way they function. Earlier models were learned only for recurring jobs, and that too only once. Then people started updating these models periodically, and now we also have systems that are designed to handle never-seen jobs before, and there are many other variants. However, all of these history-based systems lie on some common core assumptions. So let us see what those assumptions are and do a reality check on them. The first assumption is that most of the jobs are recurring. And the second assumption is that the same or similar jobs will perform consistently over time. However, stats reported in the previous works have, using industrial cluster traces, have shown the contrary. In particular, Coral and Jockey have shown that only 40% of the jobs are recurring. And there are some other stats also that show how regular cluster changes lead to a significant change in the performance of the same job over time. So violation of these core assumptions lead to high prediction error. And this reflects in the performance of the state-of-the-art history-based predictor 3 sigma. 3 sigma predicts at least 23% of jobs with at least 100% error. And for a significant fraction, the error is more than 1,000%. So to address these drawbacks of history-based learning, that is learning in time, we propose SLearn, a new approach to learning in space. Before delving into details of SLearn, let us look at this illustration that demonstrates a basic working principle of distributed big data analytics jobs. So to process big amount of data, we split it into smaller and equal sized chunks, then process them as parallel tasks on multiple machines. And when we get the individual outcomes, we merge them to get the final output. So we can see that each distributed job has a collection of intermediate tasks that are running the same code on similar sized data chunks. Hence, they are likely to show similar runtime behavior. So to capture this observation, we define the spatial dimension of a distributed big data job as the collection of its intermediate tasks. So how can we exploit this spatial dimension to learn runtime properties of the jobs? We can sample a few tasks and use their observed behavior of the sample tasks to estimate the properties of the remaining tasks or the entire job. So the basic idea behind SLearn is to learn job runtime properties by sampling the spatial dimension. In general, this approach can be used to estimate various statistical properties of the tasks of a job. In this paper, we focus on average task duration and hence the total running time of each job. So let us use an animation to understand this better. Upon a job's arrival, we sample a few of its tasks, run only the sample tasks at high priority till completion. The other tasks are kept waiting till then. And once these sampling tasks finish, we use their duration to estimate the average task length, and in turn get the total job size. Now we can schedule the remaining tasks of the job according to the job's estimated size. So now that we have seen an overview of SLearn, let us summarize and compare it with learning in time, that is history-based learning. We can compare the two approaches on 4 domains. That is applicability, adaptiveness to changes in cluster, accuracy, and prediction overhead. And space seems to clearly win in the first 2. However, we are not so sure about the prediction accuracy. In both cases, as accuracy depends on the variability in the data. And space will clearly seems to lose in terms of prediction overhead, as history is offline, but in case of task sampling, space or space non-sampling tasks will have to wait till the sampling tasks finish. So hence the 2 domains which we need to study further are accuracy and overhead, and we need to answer these 2 questions. That is, will learning in space be more accurate than learning in time? And if so, then will the better accuracy be able to compensate for the delay due to sampling? So let us begin by answering the first question. To compare the 2 approaches for prediction accuracy, we performed trace-based variability analysis. We used 3 large-scale industrial cluster traces and compared for variation for each job across tasks or space and against the variation across history or time. And one of the traces is from 2 Sigma and the other 2 are from Google. So let us look at this figure to get an intuitive idea how the variations compare. We plot this for 70 jobs selected at random from the 2 Sigma trace. The x-axis shows the job ID and the y-axis shows the corresponding variation across time and space. The black crosses in the are showing the variation in space, and the red dots are over time. To measure the variation across time or history, we looked at the coefficient of variation, CoV, in the average task length of the similar jobs. And to measure the variation across space or tasks, we looked at the CoV in length of sampled tasks of the job divided by the square root of the number of tasks sampled. So we chose these metrics based on variations these metrics of variation on basis of our analytical analysis and also results from previous works, details of which are in the paper. So we can clearly observe there's a huge difference in variation across the 2 modes. Almost all of the task CoVs are below 0.5 and the history ones are above 0.5. Now, also one can tune the performance of history-based predictors by varying the length of history. So in this figure, we plotted CDFs of CoVs of estimated job size across history with varying history durations. The different dotted lines shows the CDFs of CoVs across history with different periods, and the black curve shows the CDFs of CoVs across task and the space. So we can see that for all the history periods, the sampling across task has lower variation than history. We have also done this study for some other runtime properties and on all the other traces. Detailed results are in our paper. Okay, so we have addressed the first question about prediction accuracy by trace analysis. Now, next, let's see if better prediction accuracy can compensate for the delay due to sampling. So this question cannot be answered by trace analysis. We need to answer this by experiments. So we performed simulation and testbed experiments using a generic scheduler. We call it as GS, that schedules jobs based on estimated job runtime to optimize a given performance metric. And in our case, it's average job completion time. So we then plug into GS our sampling-based predictor, SLearn, and the other baseline predictors, prediction schemes to compare their end-to-end performance. Also, to avoid starvation, we use a multi-level priority queue structure in GS. The other details of the scheduler design are in paper. So before delving into experimental results, let me talk about the implementation of SLearn Predictor. Recall that SLearn samples a small fraction of tasks for each job, schedules them at high priority till completion, then uses their size to estimate job runtime for the entire job, and then schedules the job accordingly. Let us also talk about some of the design challenges of the SLearn Predictor. The first challenge is to ensure high priority for sampling tasks. So GS is a priority queue-based scheduler, and to run sampling tasks at high priority, we need a separate queue for the sampling tasks. However, also we don't want to further delay the small jobs, the jobs which have been estimated to be small already. So we place the sampling tasks in the second highest priority queue to strike the balance between these two options. Then the next challenge is to deal with the thin jobs, jobs with very few tasks. Since non-sampling tasks need to wait till completion, till sampling is over, this may cause unintentional delay for thin jobs. For example, a 2-task job would experience serialization of its 2 tasks. So to avoid performance degradation for thin jobs, we place a job directly into the highest priority queue if its total number of tasks is under a threshold, referred to as thin limit. And then another crucial design challenge is to determining the sampling tasks, that is how many and which tasks to sample. So note that sampling more tasks can give higher estimation accuracy, but will also consume more resources at high priority. So this will result in large jobs eating up in the resources of small jobs. And further, we also found that the best sampling ratio varies across different traces. So to balance the trade-off, we use an adaptive algorithm to determine the sampling ratio dynamically. The basic idea of the algorithm is to suggest sampling ratio that has resulted in lowest job completion time recently. And once the number of sampling tasks are determined, we pick them randomly. So these are the baseline predictors against which we compare SLearn. In particular, 3 sigma is the state-of-the-art history-based predictor, and 3 sigma TL is just like 3 sigma, but treats thin jobs as SLearn, that is, schedules the thin jobs at high priority. And Oracle predicts 100% correct size. Also, since the original cluster traces are very large, so to make the simulation and testbed experiments practically feasible, we extracted roughly 1250 jobs from each of the large trace. However, while the extraction, we have maintained all the properties of the original trace. Details of the extraction process are in the paper, and we refer the new traces as 2S trace, G trace 11, and G trace 19. So these figures show the speed up in job completion time with SLearn compared to the baselines. The baselines are shown on the x-axis, and the speedups are measured as job completion time with the baseline divided by job completion time in SLearn. So this means that if speedup is greater than 1, SLearn is better than the baseline. SLearn improves against all the baselines and performs not too worse as compared to the Oracle. And also note that the performance against 3 sigma and 3 sigma TL are similar, implying that improvements in SLearn are not primarily due to thin job bypass. Now this figure is to show effectiveness of the adaptive sampling algorithm. We plot job arrival time on the x-axis and the dynamically determined sampling ratio on the y-axis at the job arrival time. We can see that after the initial warm-up, the sampling ratio stabilizes. Detailed results are in the paper, but one thing we observed that the adaptive algorithm does not always use the highest possible sampling ratio, which is likely to give a better prediction accuracy. So for example, for the 2S trace, it stabilizes to 2% and does not go for 5%. We can see similar behavior for the other 2 traces as well. This shows that the adaptive algorithm is effectively balancing the trade-off between prediction accuracy and the sampling overhead. These figures show CDF of prediction errors observed during execution. SLearn is shown by solid blue curve and gives a significantly lower error as compared to 3 sigma. And we also compared SLearn against 3 sigma on 150 node Azure testbed, and the performance is similar. We also designed SLearn for DAGs and compared it with 3 sigma. Our approach for DAG was to combine history and sampling, and our preliminary results are encouraging with a 1.26 times improvement in average JCT. So some of the future topics to explore is how history and sampling can be combined to leverage best of the both worlds, dynamically adjust the thin limit upon the live cluster situation, and how to sample in a heterogeneous cluster environment. So in summary, we saw that history-based learning suffers from an outdated history. We propose a new and show the effectiveness of a new task sampling-based method to learn runtime properties online for distributed jobs. And we performed large-scale trace analysis, simulation, and testbed experiments. So yeah, thank you. I'm happy to take questions.